This is my final lab for Physics 2, and it covers Faraday's law. The purpose of this lab is to investigate Faraday's law by observing the motion of a magnet falling through a conductive tube and relating the induced currents to the magnet's motion. It also aims to compare real experimental behavior with a computational model based on electromagnetic induction and magnetic forces. A quick preview of my main results. In my experimental testing, I found the time it took for the magnet to fall through the tube to be 1.22 seconds. However, my computational model predicted it to be 1.128 seconds. This resulted in an error of about 8.16%. So Faraday's law states that a changing magnetic flux through a loop induces an electromotive force, what we refer to normally as an EMF, meaning that the motion of the magnet through the tube generates voltage in the conductive rings. Lenz's law explains the direction of this effect. The induced current flows in a way that opposes the change in magnetic flux, which in this case means it creates a force that resists the falling magnet. That's why the magnet goes slower as it goes through the tube. Ohm's law relates the induced EMF to the resulting current through each ring, showing that current depends on both the induced voltage and the resistance of the material. Finally, the Biot-Savart law describes how these induced currents generate their own magnetic fields, which combine to produce the force that slows the magnet's motion, as will be seen. So in my experiment, in the actual experiment that I conducted in the lab, these were my initial conditions and some pictures from that experiment. I found the length of the tube to be 0.462 meters, the inner radius of the tube to be 0.0135 meters, and then the width of that foil to be 0.0095 meters. These measurements were all needed to be inputted into the computational model. The system that I studied was the magnet and the aluminum foil tube, and the surroundings was just everything else. So in my experiment, I followed the procedure that I used the north pole of the bar magnet, and then a vertical tube I held upright and kept away from ferromagnetic materials, and then a smartphone was positioned to record the full length of the tube, and then I released the magnet from the top of the tube while the video recording was started, and I allowed the magnet to fall all the way through the tube, and then I recorded that motion for analysis. I completed 5 separate trials and found the average time it took for the magnet to fall through the tube to be 1.22 seconds. Now I'm going to talk through some of the highlights of the computational model. So overall, this code simulates the motion of a falling bar magnet through a conductive aluminum tube using numerical methods and electromagnetic theory. If we begin scrolling down here, this for loop right here allows us to model the aluminum tube as a stack of thin circular rings, each with electrical resistance determined by the resistivity of aluminum and the ring's geometry. If we keep scrolling down here, we get to this first function. This is to calculate the magnetic field of the bar magnet. To do this, we took the magnetic field formula for a dipole since we are modeling the bar magnet as a dipole. In the next function, we are using this one to calculate the magnetic flux, and we are applying Faraday's law. If we keep scrolling down, we can see that we calculate the current through each ring, and to do this we are using a combination of both Ohm's law and Lenz's law. The negative sign here represents Lenz's law since current opposes the change in flux. And then if we keep scrolling down, then we start to find the forces. So we find the magnitude of the force on the ring, and this is the force contribution from each ring. Then when we sum that, we are getting the total magnitude of the force on the magnet. Then we also have to find the force. We also found the force of gravity above in this vector, and we add that with the force of the magnet to get the net force. And then in order to update velocity and position of the bar magnet, we apply Newton's second law and use that F net. Now here is the program being run. We calculated a time that it took for the magnet to fall through the tube to be 1.128 seconds. Now, some assumptions that I had to take in this lab were that the bar magnet behaves as a point magnetic dipole, so its physical size is neglected in the model. The conductive tube is modeled as independent, non-interacting rings, each responding separately to the changing magnetic flux, and we neglected air resistance. So that 8.16% error could have came from video analysis uncertainty or non-ideal motion happening in real systems. Some similarities / differences. Both systems show the magnet slowing down as it moves through the conductive tube due to induced currents opposing its motion. Remember that Faraday's and Lenz's law. And then the experimental magnet experiences additional real-world effects such as air resistance, slight misalignment of that tube. They're not fully captured in a computational model. So finally, for my discussion, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, if the resistivity of the conductor was reduced towards zero, the induced currents would become very large. Remember that resistance is on the bottom, so that would create a very strong magnetic field that opposes the magnet's motion, and as a result, the magnet would fall much more slowly. However, what if we put holes or we cut slots into the tube? How would this affect the currents in the ring? Well, if holes or slots were cut into the tube, the current loops would be interrupted, reducing or even eliminating the induced ring currents in those regions. This would weaken the opposing magnetic force, so the magnet would fall a lot faster through the tube. So the complete opposite of the discussion question above. And then remember, this is because surface area in that tube is reduced. Thank you.